Welcome everyone. This is the 10th annual workshop of Sensam. Our last workshop, we've been in business 10 years, and it seemed appropriate that we open this thing, rather than talking about all the things that are going on currently and the number of staff and so on. I thought I'd give you a perspective on where Sensam has been, where it's come from, and what's coming next on environmental research in Singapore. So hopefully this will be interesting to you. 10 years ago, this month, I was in Singapore attending the NRF board meeting, and we were trying to promote Sensam to NRF. This was the funding decision from NRF. And it's interesting to look at the proposal for Sensam. You can see how the pitch at the time was around the idea of pervasive sensing. There's a new paradigm for monitoring, modeling, and control of natural and infrastructure systems. And the idea of Sensam was to create what you can see as a world-leading center of excellence in environmental engineering, in sensing and modeling. Environmental sensing and modeling. And to demonstrate all of this in Singapore. What I want to show you over the next 20 minutes is what we've done to make good on this. Same meeting 10 years ago. We said that the challenges we were dealing with were multi-scale challenges, and that the research we would be doing would be dealt with at different scales. There would be microscale developments, meaning new sensors were needed, and new platforms for various forms of exploration. We talked about mesoscale developments, sensor networks and the like. And we talked about macroscale work, which relates a lot to the assimilation of data from remote sources and local networks, and coherent large-scale environmental simulations. Some of the other words are probably less relevant. We also promised various deliverables, and you can see in red, I've shaded out in gray because I'm not sure that's so important, but you can see the kind of deliverables we had in mind for Sensam. As you know today, Sensam's activities are sort of divided in three sort of pillars, one dealing with climate, one dealing with urban, and one dealing with marine situations, and there are many projects that we're currently operating. As you are aware, we're working a lot on regional climate change and land use and paleoclimate, on urban atmosphere, water quality, and urban infrastructure, and on sensing in the nearshore environment and the coastal environment, and quite a lot of marine science work. So this is the sort of scope of our activities today. And as you're aware, we're quite a large group. We're still about 145 researchers. The one number that you should probably be aware of is the number of graduate students is shrinking as Sensam comes to the end of its 10-year cycle. So this is the sort of state of affairs and the state we started from. It's interesting to look at the 10-year history of Sensam as we proposed it, starting in sort of summer of 2007. What was going on in Singapore at the time? There were actually two organizations or two research communities in Singapore that were dealing with environmental matters. One is familiar to many of you in the room as the Tropical Marine Science Institute at NUS, which is a soft money organization doing mainly contract research, but was focused heavily on marine science. And at the time, there was a partnership at NTU with Stanford University, which was simply called SSP, and this was a sort of educational program, rather like the SMA program at MIT, and was focused around water resources, and it was coming to its conclusion when we set up. Concurrent with our setup, there was also a third organization that just started, was a collaboration between NUS and the Delft. So this was a second large water activities. Is this a pointer? Oops, I've turned something off. We have a laser on this thing? Middle. Oh, yes. So this was the Singapore Delft Water Alliance. So these were the activities going on at the time. As we set up here in Singapore, two other activities, both at NUS and NTU, concurrently were going on. At NTU, they set up the Earth Observatory of Singapore. This was about the same time with Kerry Sear. It was the first plan to hire faculty, so they had 0 faculty at this point. At NUS, they formed NERI, the Environmental Research Institute, which was really an umbrella research outfit of the type that we have at MIT, with a lot of existing research coupled under this NUS institute. As time's gone by, the NUS NERI Institute has co-opted a large part of CREATE through the E2S2 program, which is the collaboration between NUS and Shanghai Jiao Tong University. And we have a lot of interactions with these groups. I should say we have a lot of interactions with TMSI also, and with the Earth Observatory. And at NTU, we've seen the creation of CELSI. This is the Life Sciences Institute that's formed at sometime around 2011. And these have all been subsumed in the first department of Earth Science in Singapore, the Asian School of the Environment, ASE, sometime around 2015. So you can see that the growth of the community, the research community environment, is quite strong at the two main universities at this point. The color coding is all very cunningly organized around the colors of NUS and NTU, as you can figure out. It's also very interesting to notice that when we started CENSAM, there was no such thing as an environment agency in Singapore. Environment was handled through a bunch of different agencies. In fact, at the first one of these meetings, the first annual workshop, the head of NEA came to visit, and they were just setting up as a regulatory body. And NEA became very actively involved in climate research somewhere around 2013. So in fact, our research in climate predates any of the government actions here. So we've been a precursor for a lot of environmental work in Singapore, both in seeding activities in here, being engaged very closely in here, and engagement with CCR. Singapore, of course, has changed hugely too over the last 10 years. You can measure Singapore's progress by Marina Bay. I remember when we first came here, we said all kinds of things are going to happen at Marina Bay. I don't know if we really understood quite what. I mean, in 2008, they opened the barrage, so they turned the river into a lagoon. 2010, they opened this Marina Bay Sands and the casino, all on reclaimed land. 2012, they built gardens by the bay. And if you were to sort of extrapolate this to the whole of Singapore, we could talk about new towns in Punggol, new subway lines, and so on. Singapore has been a very, very busy place over the last 10 years. Environment has really sort of raised in the consciousness of Singapore through events that have occurred. And many of you will remember in 2011 the flash floods, some of the most serious flash floods in Singapore. And those of you who are here in the summer of 2013, the Haze events. And these things have not been disconnected from CENSAM. CENSAM has evolved and adapted, trying to figure out where important environmental issues were affecting Singapore. In fact, I looked back through all the 10 years and I noticed that we actually didn't start out looking at peat forests. One of our signature programs on peat forests came about from a perception that this was an unchecked or uninvestigated problem, where land use in Indonesia in particular was destroying the last big stands of tropical peat forests in the world, potentially releasing a lot of carbon into the atmosphere. And this was where this work really first started. We also didn't start out doing climate modeling. Climate modeling wasn't part of our original agenda, but we could see that the global climate models were providing very little information on what was likely to happen in Singapore and the surrounding region. And primarily because the land mass in this area is as a maritime continent with islands, numerous islands with high topography, and very little resolution, therefore, of climate in this area. And this is some work from FTL to here, sort of showing in the future scenarios, which we'll talk about the frequency of very large flooding events like the one we saw. So we've done a lot of work on regional climate modeling. And most recently on air quality, of course, has become a very big issue here. And we've worked both on local issues. For example, Eric Velasco's worked on exposure to the PM 2.5 fraction for different modes of transportation. And most recently, Stephen Barrett has been looking at the apportionment of the PM 2.5 fraction across the island, showing that it's not just the biomass burning of peatlands, but also a lot of domestic sources contributing to this. So we know that challenging air quality improvements in Singapore involve both local challenges as well as transboundary challenges. When we started 10 years ago, in fact, none of us had worked in Singapore, with one exception, Ola Madsen. And famously, Ola wanted to work on sediment transport. This is his area of expertise, a unique problem in Singapore, a country where land reclamation has been hugely important. So CENSAM started big, we built this giant flume with pumps at either end so we could study exquisite details of the flow of a fluid over a sediment bed with currents and waves and so on. So this was a remarkable facility. In fact, it's a prototype of what may happen to a lot of other facilities as CENSAM moves towards closure. This facility was in fact installed at NUS, was run by CENSAM for many years, and is now being transferred, and NUS is now using it with Jing Yuan as the student who is now on the faculty at NUS. As expected, it's produced exquisite results which have proved or validated various theories on wave-current sediment interaction, and Ola Madsen has given talks which can only be described as entertainment as well as anything else. So his monster in Singapore has made the rounds. So we've started with problems of relevance to Singapore. Other people have been working on similar sort of issues relating to land reclamation, notably Eric Adams, who's been working on barge sediment disposal, which is where you have plumes of sediment falling through the water column. And they've worked very extensively to build up the fluid mechanics and understanding of these processes so they can be better applied in practice. And this is an example of a piece of work where not only is it generating a lot of interesting engineering results and scientific results, but they've now got a piece of open source software which is available to everyone and is being used quite widely within the reclamation and dredging communities, which of course is the large user base for this work. Famously, on the first floor of the lab building, we have a fleet of autonomous vehicles, both the kayaks, the surface water vehicles, and the underwater vehicles. Over the years, we've added all kinds of imaging units to these, from sonar, autonomous samplers, multi-scale water quality, holographic imaging. This is from George Barber-Stathis' work, all done under this auspices of the Wave Lab. This has been a means for us to explore the marine environment and tackle various applications of interest. If you look at the work of the Waves Lab over the years, it involves large field trials where they do both robotic improvements in the robotic control and navigation of these vehicles, and also they've done supporting work for particular applications. So you can see there's quite a lot of work on algal blooms recently. There's also validation of a lot of the sensors that have been tested out in the lab. When this first started, it was involved in sort of underwater detection of structures, for example, a jetty structure here. It was involved a lot in tracking things like contaminants and thermal plumes, and this is a trace of a thermal plume coming from one of the power plants here. And as I say, most recently, you'll hear from Sandvik Leong about harmful algal blooms. We've also looked at novel ways to do sensing in the marine environment and new sensing paradigms. This is work which Dick Yu has become involved in, using what I've called the Dick's flower pots. These are these autonomous tubs with sensing capacity and mobility, which you can deploy very quickly. They can communicate with one another, they can compute, they can make measurements, and potentially they could actuate on various problems. A novel kind of sensing technology. We're seeing somewhat reduced versions of this. E2S2 is also involved in what they call SWAN project, which has got some elements from this. In terms of sensors, the most sophisticated sensing elements that we've developed start with the work of Harry Hemond, working in collaboration with TMSI and Kelvin Ng, working on LED-induced fluorescence. We've actually embedded these in AUV vehicles, which has enabled us to track, for example, chlorophyll. It's an interesting chlorophyll inside reservoirs. So you can see the tracking in space of an online sensing measurement here, and a temporal resolution of chlorophyll too. Very useful technology, ready for licensing, and there's been some attempt to get startup going on this, and more recently it's moved into the territory of air quality using similar kinds of approaches, optical technology. More exotic things have come from biomimicry. Mike Triantafilo and Pablo Valdivia, have worked a lot on biomimicry, for example, both for propulsion systems. This is the robo-octopus, which I find fascinating, and this is the seal whisker, which have allowed a lot of new advances in flow measurement, for example, for both for vehicles and for other applications. Most recently, the fusion of these biomimicry with MEMS sensor capability has moved more into chemical contaminant sensing. And with Ajay Kotapalli, they've been working on the HEMT sensors for picking up heavy metals in water bodies and nutrients. So these designs, these sensors, these MEMS sensors, have also gone through testing on the autonomous vehicles out in the marine environment. So this is also a very promising new technology. Coming out of all these sensors, we're seeing startup companies. This last year, there's a company called Sensonomics, which was founded by Ajay Kotapalli, Jianmin Miao from NTU, and Michael Triantafilu. This has now got money from SG Innovate to pursue its applications. They're looking a lot at MEMS flow sensors, very small flow sensors. And in fact, some of the applications are outside the marine environment. They're more in the realm of medical sensing of flow. For example, in IV drips and so on, where you need very low cost, very accurate flow sensing. Seems like an appropriate point in time to say another aspect of Sensum has been the creation of future leaders in academia. This is a group of 12 people who are all graduates of Sensam, who are all faculty members today. And I think I was told almost half of them are now tenured faculty members, which tells you 10 years is a long time. So congratulations to all them, and it's very nice to see quite a number of them back here today. Turning to the big scale, or the smaller scale, the regional climate and the modeling aspects of Sensam, the things that have interested us or started to interest us were understanding the rainfall pattern, the seasonal rainfall patterns at higher resolution. You can see that Yoon Sung, in fact, has done a lot of work building up this regional climate model to provide a more accurate predictor of the satellite images of rainfall across the maritime continent. This kind of information, of course, leads directly into simulations of predicted frequencies of daily precipitation. For example, in the Malay Peninsula, you can see the data in red. You can see the global climate model is simply underestimating the magnitudes of extreme rainfall events. And you can see the regional climate model doing a much better job. This is looking at the past history. As you go forward in time, you're then able to extrapolate with the regional model and predict these extreme events, 150 millimeters a day, which would have caused the flash flood, occurring with a certain frequency. You can see an annual frequency here. So there's been work on frequency of heavy rainstorms, a very important thing in this area. There's also been work done by Paola Rizzoli on coupling of atmosphere and ocean modeling. And I just wanted to point out this is further, once you get into the world of climate modeling, you're backtracking and sorting out your models from the past history and then extrapolating forward. Paola's modeling work here, you can see very high resolution meshing of the ocean in the area around Singapore. This is the shallow South China Sea. And then you can see the sort of predictions that you make for various climate scenarios. So this is looking at sea surface temperature, for example, in 2094, a long way ahead, I think. RCP is the 8.5. This is business as usual. So no one changes their use of energy or man-made carbon into the atmosphere. The worst case scenario, I suppose. And you can see the regional climate model or the regional modeling achieved by the regional climate model and FVCOM, the fluid model. And then you can see versus a global model. And the reason that this figure's been shown is to sort of illustrate for you that around Singapore we don't have much resolution from the climate, the global model. You can see the white spots are no resolution at all. Singapore is a dot here, so you can imagine we don't have very much information. And you can start to see the predictions coming out of the regional climate model. I told Paola that this probably says it's not going to get quite as warm as we fear, but if you could read the scale, you'd realize it's another 6 degrees Celsius on the sea surface temperature in the South China Sea, which I don't think is good news for anybody, and I'm sure has huge impact on marine life in the South China Sea. So we better hope that RCP 8.5 doesn't happen. Chen Wang has been doing an awful lot of work on regional climate also. He's worked on a number of things. Recently, he's been looking at aerosols and coal burning in Asia, looking at how that affects rainfall across Asia. And he's also been looking more recently on the air quality, trying to understand how low visibility days are changing in Singapore associated with fire emissions and with local sources. So you get a sense of applications of these climate regionally affecting Singapore. On the science side of climate change, we learn a lot, of course, by studying the coastal waters. Ed Boyle, who joined us in a later phase of Sensam, has led a lot of work on looking at lead isotopes in the Singapore region, and discovered, to his amazement, that in fact his technique that he's developed and is famous for, looking at the isotopic ratio of lead between 206 and 207, there's a huge discrepancy in what he finds in the coastal waters in Singapore, showing in fact that the aerosols are not the primary source of the lead in the coastal waters. And this has led to a huge piece of research to try and evaluate why. And in fact, it appears that natural riverborne particulate materials may be a lot of the source of lead in the region. This work has also expanded very dramatically. It's involved a lot of sampling campaigns. You'll hear later, I think, from Gonzalo Carrasco, who's been doing a lot of this work. The work has shifted more in the bioavailability of metals, which is going to affect the biogeochemistry of the whole area. It's a massive field campaign done jointly with people at EOS, so it's again an example of Sensam collaborating with EOS, involving a large number of students and researchers on regular field campaigns, both locally around Singapore, up the Johor Straits, and across the South China Sea. Another big field project related to climate is the tropical peat forest work. This has been really an extraordinary effort because we've had to build testbed sites in the pristine jungle in Brunei. This is the first of its kind anywhere in the world. Really, it's been enabled, again, by a collaboration of Charlie Harvey at MIT and Alex Cobb here. It's involved a collaboration of just about everyone you can name. So it's worked with people from NTU and NUS, University of Brunei, research engineers, intern students, high school students, a field crew who speak something or other, Dayak or something. I think Alex communicates in multiple tongues. And it's all worked. It's all come together. It's a remarkable project, but it's taken a very long gestation period. There are very interesting results coming from this about the formation and history of peat domes, how the peat dome grows, and how the water table controls the emission of carbon dioxide from the surface. June 2017, at last, they've published a phenomenal paper in PNAS. And if for the young researchers in the audience, quality matters more than quantity. And nothing exemplifies this more than this piece of work that's just recently been published and will stand, I'm sure, as a legacy for this project for many, many years to come. So it's very exciting to see a piece of science come together like this. The interesting thing of this work is by understanding the peat domes, we now have potential new ways of predicting flammability and carbon fluxes, and of controlling them by managing the drainage in the peatlands. So this opens up a whole new world of how one might figure out how to control effects of haze from peatland fires or try and mitigate these problems. In the urban context, there's a huge amount of work done at Sensam on urban heat island effects. Les Norford has been the prime agent behind this work. And this is just a summary here of urban heat island with and without anthropogenic heat. The yellow scale, they're not the same scales. I just want to point out that different parts of the island have different urban heat island effects. This problem has been studied very exquisitely, so we have a lot more data on urban heat island effects, thanks to the research at Sensam. And this expertise is in fact contributing to a project which is looking more at the management of urban heat or cooling Singapore. This is the first big intra-create project which started this last year. Sensam is part of this, along with SEC, the Future Cities Lab, and with TUM Create. And you can see that this is the work that's being done here is largely related to mitigation measures. I should also point out, while I have the opportunity, one of the PIs is Zhang Li, who was one of the first researchers who have been promoted to a principal investigator within Sensam over the last 10 years. And you're going to hear a lot more about this from a presentation of Heiko Eit later in this session. I've been involved in a project which monitors the water distribution, the pipes beneath our feet. This started out and moved very quickly. We were primarily interested in controlling water losses. We ended up doing real-time detection and localization of bursts and demand management. The project really, here in Singapore, was enabled by the collaboration with PUB. So that collaboration has been a working collaboration which has lasted more than 8 years. It's ultimately resulted in us monitoring the whole of Singapore. So Singapore is the first city in the world with a smart water network for looking at these classes of problems. It led to a commercialization of the company Vicenti, which essentially started doing commercial developments in 2013 and is in all these cities now, plus some, I'm sure. And the development since last year is they were bought. They've grown. They employ the order of 30 people in Singapore, and they've been bought by Xylem, which is one of the largest water companies in the US, listed on the New York Stock Exchange. And they're proceeding, as you can see, to work on smart water systems. And this is propagating everywhere around the world now. My research is now moving in, as you'll hear tomorrow from myself and Dan Cheng, is working more on microbial communities and water distribution systems. And the update on this is we've put smart water networks around the NUS and NTU campuses. And these are online as of the last month. So this is very recent stuff. The final thing I thought I would sort of highlight to you is a very interesting new project that we've gotten involved in. And this comes out from last year's workshop here. Last year we were approached by NParks about the problem of trying to manage what they call the health of urban trees. Singapore, of course, is a city in a garden, and it has actually more than 2 million planted trees. Who knew? And the idea is they would like to do remote sensing of the health of these trees. The work we're proposing to do on this involves both satellite imagery from multispectral devices and higher resolution measurements from airborne, UAV, and terrestrial measurements using hyperspectral images and LiDAR. This is the basic scope of this. To me, it's very interesting because when they first came to us with this proposal that we might think about, it didn't seem very obvious that it fitted in with Sensem, except that, of course, it is environmental sensing and modeling. And what's interesting to me is it really demonstrates the interdisciplinary expertise and skills we have within Sensam, because it turns out we have experts in radiative modeling, we have experts in remote sensing, we have experts in robotics, we have experts in plant physiology. It turns out this was uniquely suited to a group like Sensam. So we've been very able to respond to this. I should say it's really enabled by the fact our research staff have stepped up and taken the initiative to make the connections with NParks. And I particularly want to acknowledge Chiang Gang and Vivek for doing this. And we now have a big project with NParks starting for the next 2 years. I probably should skip over the details of this because there's a lot more to come and we haven't done any research yet. Finally, I thought I would just apologize to those I haven't covered. I've missed some of the projects, but finally, I just thought I would pick up on NRF's expectations for CREATE. Please read the words carefully. This is NRF and this is CREATE. We are part of the CREATE campus. And you can see that NRF, when it established CREATE, and we were one of the original programs within CREATE, was to do a number of things. First of all, to do outstanding research. And I hope I've demonstrated to you over the last few slides that we've done some really outstanding research and published some great papers, patents, and so forth. It says to make this a second home for overseas partner institutions, and I think we from MIT have been very actively engaged in Singapore through this, so I think we've met that criteria. It's to establish engagements in Singapore with deep engagements and collaborations with local universities, and again, I think we've met that metric very thoroughly. The joint supervision of students and research staff, again, I think is a very big success story in Sensam, and a place where agencies turn when they've got solutions to difficult problems. Again, I think we've met that metric. The reputation, well, that's to be seen by others, of course. We can't talk about our own reputation, but I think we're very widely known. Singapore is much better known for environmental research than when we started in 2007. So I think Sensam has been a very effective contributor to the mission of CREATE over the last 10 years. Finally, can't resist, probably not many of you are aware, not only are we innovators in our own research work, our administrators are innovators too. And I should acknowledge Vera Blanc. She's just won an innovation award to develop the administrative tools that make my life and everyone else's life very much easier. It turns out that you would think there would be all kinds of project management tools or program management tools online and available. There are lots of large companies to do this. It turns out there's a real niche for this within academia at organizations of a different size. And these tools are really very sophisticated. Censem has some very nice tools that it's developed for managing the project. Far better than I've seen anywhere back at MIT, I should add. So I wish her luck. This is an opportunity for her going forward. And finally, I just should thank everybody who's participated. In particular, I'd like to thank the organizing committee for this particular workshop. And this is Kiangwei Chen, Megali Bora, Alex Cobb. I know I'm missing somebody. Rajni Kaushik, thank you. And Janelle Thompson, who's put the whole program together. I think we have a very interesting program. I hope you have a very interesting day or so with us and join us for the banquet on Friday evening. Thank you very much. If there's a pressing question, Les is going to come up.
Good afternoon, everyone. I'm Janelle Thompson. I'm the session chair. And I'd like to take this moment to thank Andrew for that great intro or overview presentation. And now I'd like to introduce the following session. Today, we're going to start off with a session on thermal comfort and air quality for livable cities. Urban sustainability, as many of you know, is one of the main themes for Singapore's RIE 2020 plan. And in this session, we're going to focus on several topics closely related to urban sustainability, including urban thermal comfort, urban heat island mitigation, and urban air quality. We're going to start off this session today with Professor Leslie Norford, who's going to give an overview of the research projects undertaken by Censem in this area. And this is going to be followed by a presentation by Dr. Heiko Eit from SEC, who is the project leader for the Cooling Singapore project. This is the IntraCreate project. We'll then have presentations on numerical modeling for understanding the urban thermal environment by our postdoctoral scholar, Negin Nazarian. And on the air quality side, we'll have a presentation from Eric Velasco and Professor Jason Cohen, who's joining us from his position as a faculty member at Sun Yat-sen University in China. Jason, as many of you know, is a Censem alumni, so we're very pleased to have him here. So following these 5 presentations, what we're going to have is a 15-minute Q&A panel. So as the speakers change, we'll allow a couple of questions immediately after the talk, but we also anticipate that there are going to be some questions that will span the different presentations. And so we'd like to ask you to hold those until the end of the session, where we'll invite the speakers to join us on the stage and moderate an audience-driven Q&A panel. And so with that, I would like to turn the stage over to Professor Norford. Thank you very much.
Thank you, Janelle. Well, welcome everyone. It's a pleasure for me to be here and summarize some of the work that I have found especially maybe significant, exciting, and done by just a great group of people whom I greatly admire. Some of them, but maybe not all of them, listed here. There's going to be some amount of detail about our work, but I have maybe 3 overriding themes here. One, the importance of data, and where I think Centsem's been especially strong in this area. Some of the physical understanding we've gained from the measurements and models, and then some emphasis on who uses the models, making not only our data but the models widely available to practitioners as well as regulators. So Andrew touched on a little of this before, but what temperature? Temperature is one part of thermal comfort that Negin will talk about in more detail later. What you get depends on when and where you are in Singapore. This is a land use map, and we've all traveled around here some and have some sense of the variety of terrain. We've, in our work, have relied very heavily on data that our NUS colleague, Matthias Roth and team, and our research scientist, Eric Velasco, have gathered over a number of years. So this is a world-class data set, and particularly in the tropics. The dots here are temperature sensors, not from government sources, but from Matthias's own network of temperature and humidity sensors, some rain gauges from the government, and then a flux tower here for in a low-rise residential area for sensible and latent heat fluxes and carbon fluxes that we've maintained for many years. And so this is the bedrock by which we validate our models and establish parameters for them as well. So some of Matthias's early work, done about the time, just about the time we were getting started, highlighted several areas, a rural reference in land, rural, undeveloped land used by the military, an HDB area, high-rise residential, low-rise residential, central business district, and this is commercial area. This is kind of Orchard Road, as just exemplars of the places where we have good temperature measurements. And what's come out of that is results that show the temporal and spatial variation of temperatures throughout Singapore. Okay, so these are averages over a diurnal cycle, and the highest are Orchard Road, maybe no surprise, over the year about 4 degrees. HDBs at the lowest. Okay, if we then look, there's a seasonal variation as well with the rainfall patterns, and then some variation just among measurements, and where the biggest peak in that year was a little over 7 degrees. And you look at Orchard Road and you say, well, there's some clue why it's the anthropogenic heat as one of the factors, in addition to, say, lack of vegetation and building materials that determines urban heating. Okay. So schematically, we say we're, maybe growing up, we say, well, we're inside or we're outside. And in an island like Singapore or in cities, outside isn't really undisturbed outside. We live in a boundary layer, and outside is a product of what we're doing as much as weather patterns at a kind of a regional level. So we're literally down in the weeds. And to model that, we have to account for not only what's happening at the city level, but what is happening, what's forcing it with the local, the regional environment that affects that. So Xiangjiang Li and our staff spent about 2 years working with a regional model, WRF, to develop something that I think is still unique in Singapore that can give us, say, island scale sort of average impacts of a lot of effects on the urban heat island. So this is a nested model with five one-way nesting. This is the lowest level here with the commercial areas, low-rise, high-rise residential, and then commercial industrial. The model at the lowest level that determines the energy balance is simply a nodal, say, thermal model with sort of lumped resistances and storage elements in the ground and in walls and communication to the atmosphere above. This is the temperature that's a kind of a construct. It's the outcome of everything else, and this is the temperature in the single-layer urban canopy model that comes out of things. The energy balance here is pretty simple. What are the inputs? If we look at this as a control volume, there's net radiation, shortwave and longwave in minus out. There's us, the anthropogenic heat from buildings, traffic, a little bit of metabolic heat. Where does it go? Sensible heat flux, latent heat flux, and over roughly a diurnal pattern around here, storage in and out of this control volume, including the ground down here. We'll have a little more on the latent heat flux in a minute. That's been particularly interesting. So how big are these terms? And if we look at commercial industrial, or the other two, the anthropogenic heat, this is watts per square meter of ground area. Here's the net solar, so it's about 100 watts a square meter net. And in commercial areas, the anthropogenic heat is a little more than 85% of that, much less in the HDBs and the low rise. So in commercial, the takeaway is we're putting about as much heat into this control volume as we're getting from solar radiation. So with that understanding, if we look at the plot, revisit the plots that Andrew showed, it's no surprise that for this, the commercial industrial area, the average increment at night of temperature due to our activities and just the nature of the built environment is 2.2 or so. And if we just throw the switch in simulation and get rid of it all, then we're down a little less than half of that. The anthropogenic heat is about half the net solar. Those are the inputs. And if you take away that, you're getting about half of the 50% reduction in the UHI effect. And then there's a spatial variation to this as well that I won't discuss at night and in the day. So this kind of variation is important for the kind of work that Heiko is going to talk about shortly. If we want to look at mitigation of the urban heat island effect, reduction of temperatures, we need to evaluate techniques spatially and temporally. Jeanjang's also looked at green roofs and cool roofs. Now, these have been studied at individual building level. I think this is among the few studies that will do that at the level of an urban area. So cover all the roofs with more reflective material or with vegetation. And this is the change, the reduction in daytime temperature. So it's a little over a degree here for widespread use of cool roofs and a little less than that for green roofs. So these are helpful to regulators in assessing if we go all out in any of these areas, what's the maximum impact we can expect from them. On the cool roofs, Jeanjang also looked at the slight increase in humidity, which works against thermal comfort, and found that on balance, the reduction in temperature outweighed the increase in humidity and gave us a net benefit, modest benefit in thermal comfort. Vegetation, we've used Eric and Matthias's flux tower to keep us honest on the latent heat flux and have improved the models of vegetation, particularly for trees. Without that, here are the data, Eric's data, and our models before Jeanjang and Liu Zhuan started on this were not very good, particularly in dry periods. And those models have gotten, the red solid line is our current models where we've done a much better job of accounting for the evaporative processes. Okay. I want to spend just a couple minutes on one technique we've looked at recently to tackle the anthropogenic heat. So we're not going to just turn off all the power plants in Singapore. What can we do? One aspect we looked at was in HVAC, an area that's where a lot of my work has gone. And the idea is this. A lot of the cooling in Singapore is used for dehumidification. No surprise for those of us who have spent any time here. And the process that we've done that by for 100 years, HVAC people, turns out to be pretty rotten. Take the Coke can out of the fridge and water condenses on it. This is what Willis Carrier did 100-some years ago. We condense water out of an airstream, and then we throw that cold water down the drain. The heat of condensation is quite high. So anybody who works in the desalination area would say that is really awful, about 2 orders of magnitude more awful than the thermodynamic minimum for producing water. And so we've picked up on some of that with our Sensum colleagues who have just recently started working on that. And this was a project well, here's one way of doing that, and that's to use membranes. Membranes can remove water vapor without condensing it, and so you get the benefit, well, you avoid the energy of condensation. And we came up with a system of doing this. This is 2 MIT grad students associated with Sensem, one from Professor Lienhard's group who works on membranes for a living, and one from my group who works on buildings for a living. And they cooked up something where water vapor can be removed from a membrane here with the vacuum pump before it goes through a heat exchanger for cooling and into a building. And on the way out, it can be put again across a membrane into the airstream that's going out, which is at lower vapor pressure because it's been cooled. And this is something for which we filed a provisional patent, which is being prosecuted from the NUS service. And it has a COP of kind of you get 10 units of cooling out of this, of dehumidification for every unit of electricity, which is really pretty good. Okay, let me come back to data for a couple of minutes here. This is the work of Tiangang Yin, whom Andrew mentioned. We've been waiting a long, long time for sort of high-quality data about the built environment in Singapore. Zhang used some 5-6 years ago for his WRF model that took some effort to get, and it's now somewhat out of date. So where do we go? The government's still working on a virtual Singapore plan to make this available to agencies and eventually researchers, but we reached a point where it was holding up our work in various ways. So Tiangang went out and negotiated the purchase of a digital surface model from a Japanese firm. Here's the island, and you get all the surface features. This is 1 meter resolution. And from that, you can filter out all the large changes in slope that could be trees or buildings to get a digital terrain model that's shown here. So let's show you what we can do with this at the scale of the NUS campus, where there's some interest in having sort of a virtual campus model. Okay. Here's the digital surface model. Here's the digital terrain model after we've removed all the trees and the buildings. Okay. If we take the difference in those, we get heights of the objects, the trees and the buildings at again at the 1 meter resolution. That's pretty good. We can now overlay with that the building footprints that come from the Singapore Land Authority or OpenStreetMap, and we can get our mitts on those data. The government doesn't hold them back from people like us. And so if you put that all together, then you get the heights of the buildings throughout the NUS campus. In terms of where we do our work, we're down here now some. Here's the Create Tower. Here are all the low-rise black and whites next to us and so on. So again, the resolution here is pretty good. We can extract the height, and then we can add that back onto the digital terrain model and get the overall heights of the buildings above, say, above sea level. Okay. So what do we do with that? Well, one thing we can do with that is classify all the land in Singapore. You know, we talk about urban heat island effect and say, oh, this is urban and this is rural. The profession's moved on from that. I mean, how dense is urban or rural? And so now there's a land surface local climate zone classification scheme for this sort of thing. And with our mapping and with Landsat satellite images in different bands, we have constructed a local climate zone map for all of Singapore, which will give us a sort of a world, a reference for our work that the rest, the global urban climate community understands. So this has the impact of vegetation and different building heights in it. And I've listed a bunch of other things we can do with this. It'll affect our mesoscale models. When we go down to microscale, we have better information about the buildings for our CFD models, energy balances, the sort of work that Megan will talk about on thermal comfort, and some work on estimating vegetation volume that we're starting to do with SEC. All of this builds on the data set that Tiangang has obtained and worked with. Okay, a couple more things. I want to show just mention 2 examples where we have combined data that we've obtained and built models on them. This one I'm not going to show in any detail, but here we wanted to understand better airflows in urban canyons under low wind conditions, where if one surface is hot and one is low, you can get a recirculation flow that can help transport pollutants out of the canyon. We didn't take measurements in a real canyon. That's kind of difficult. We made our own out of shipping containers on the NUS campus. Okay, 5 minutes, thank you. We visualized the flow with some theater fog. I won't give you the results of that, but we just have some very interesting correlations that allow us to predict this sort of thing. The other thing we did was look at airflow in void decks in Singapore. And real briefly, the idea here is how much airflow do you get under those? Singapore isn't doing as much of those in HDB. Do they have some value? So one of our students, Lukwai Chu, measured this in the Civil Engineering Hydraulics Lab, Mira Ola Madsen's Monster. This shows the agreement of experimental data with a CFD analysis he did. This is sort of a blow-up of that. You get higher flow underneath here, particularly in the early ones. And then he built a 3D model of this so we could have with streets as well as canyons in between, sort of a 3D array. And interestingly, what we found and hadn't expected was that if you're moving along in the canyons, yes, if you have void decks, you get more flow than if you don't. But if you're in the streets, you also get a lot more flow than if you don't have void decks. And that's just due to overall reduction in flow resistance in the canyon. So this gives us some insights on say, urban design problems. Okay, just a couple more things here in the last 3 minutes. I'm going to zip through these, but the point here on all of them, and I'll skim, is who owns the models? Who gets to use them? Is it just researchers? Does it just go to government agencies? Or can we provide models that practitioners could use? And I'm very much an advocate of the latter, that innovations in urban areas are going to come from students, from architects, from engineers, from people in practice, as well as regulators. So in this one, this is a means of estimating urban temperatures with a nodal model and some representation of the simplified representation of the atmospheric processes. We've tested this with data in Singapore, again, Matthias-Ross temperature data, and in European cities. The agreement's pretty good. The sort of thing we can do with this is also say, well, if it's hotter at night in an HDB area, how much does the energy used for air conditioning go up? And this is being incorporated in sort of open source tools for designers within the kind of CAD framework that designers use, the Rhino CAD program. And the tools are available on GitHub. And more about that in just a moment. We're doing the same thing for airflow. We have a simplified CFD code using the Lattice-Boltzmann method. And the code itself isn't as important as just keeping the whole thing in the designer workflow. If someone's saying, how do I move buildings around? What if I do that? How does it affect airflow? Not having to go out to a CFD program, mesh it, run it, get the results, import them back and export them back into something. We speed up the process by being very careful about the wind profile we're using, and we get that from the sort of the density of the urban area. And very careful about minimizing the size of the simulation domain, so it's large but not too big, and relying on some theory from others to estimate that as a function of the size of the built environment. So here are the buildings, an architect could do this, and here are the results in a section and in a plan of airflows. This is the visual scripting language we do to glue these components together. And the very last one that Ken-Wei Chen, one of the workshop organizers, has done is at the urban level, okay? Maybe you have a Topio sort of thing, or a spine or a grid thing for an urban neighborhood. How do you mask the buildings? How do you vary the height for daylight or PV, or to minimize solar heating on walls? And how do you run through a bunch of cases to try to pick out the best ones? He set up a selection of tools to do this, that start with various inputs from OpenStreetMaps or master plans, and then eventually producing a city GML map of the same thing, and then something that might have PV energy or daylight availability. Okay. And the glue that holds all this together are his Python libraries. And then we can do an optimization that produces some sort of Pareto front of best case things. So this is also on GitHub, which in a way has become an archival method of choice. We can put our code up here, and anyone in the world can access it. And they are using it in some of the cases. The Urban Weather Generator is getting a fair amount of use in this regard. So this is Ken-Wei's code to sort of glue all these other pieces together where models come from different code and then help the designer produce useful results. So with that, I I thank you. As Janelle said, I can take a couple of questions while we're getting the next speaker hooked up, and otherwise I'm happy to talk in our panel session or the break or whenever you can get me. Thank you very much.
Are there any questions for Professor Norford?
Oh, you're in shut it. Okay.
All right.
I need to close.
Yeah. Okay.
All right, thank you. Up next, we have Heiko Eit from Singapore ETH Center. Thank you.
Good afternoon, everybody, and thank you for the introduction. As already been mentioned before, Cooling Singapore is the first intra-CREATE project, and I think we actually have a very nice representation of CREATE because we have the three major or the three biggest CREATE entities involved. The Singapore ETH Center is leading this project, and then of course there's SMART involved. And we also have TUM Create involved, and we also have NUS. So it's actually quite a nice, I think we have quite a lot of expertise here. So what I'm going to do is, I'm going to give you an overview of the project and what we are planning to do mostly, because the project has started about 6 months ago, so I can't actually talk a lot about findings and outcomes because it's sort of in the progress. But I hope that at the end you have an idea of what Cooling Singapore is about and what we're trying to do, because in many ways it's not the, I would say not the sort of standard kind of academic project with a lot of focus on academic publications. The project is very much about policy, roadmap development, and Urban Heat Island Task Force and R&D roadmap. So I will talk about this a bit more later. Yeah, the urban heat island effect, I think I don't need to go into details. I think Les did a great job explaining this already. But one thing that I would like to highlight is that there's no such thing as a Ministry of Urban Heat Islands. I mean, I've just learned that the NEA is also not exactly been around for that long. And there is no agency or no ministry really sort of the one that is responsible for urban heat islands. So this involves a number of agencies. And this is, in the early discussions of the project, especially also with NRF, one of the things that came up is really that it needs a combined effort from multiple stakeholders. And getting these together and coordinating these efforts is actually a major undertaking. And I'll mention this later, but one of the main deliverables, in a sense, that we have in the Cooling Singapore project is this Urban Heat Island Task Force, which is sort of trying to, be kicking off this kind of coordination effort. This is just sort of what happens if the Singapore's population go up, because there has been this, this population white paper a couple of years ago, which also caused quite a bit of an outcry. This is not exactly a very scientific extrapolation, but I think it gives you an idea of what happens if we add more people to Singapore. At the moment, at least in here, we are on the tropical hot wet line, and at the moment we have about an urban heat island effect of about 7 degrees. And if you add more people to Singapore, as I said, the population white paper spoke of 6.9 million, but if you talk to different people and different agencies, and there's also larger numbers already in discussion, and then you can easily see where things are heading. So for Singapore, the urban heat island effect is obviously important if they, since they have intentions to grow. Another thing is, I don't know whether you've seen this, this was an article on the Straits Times. It was actually published in other newspapers as well just recently, and that was based on this work by Estrada, Boatzen, and Toll, and they have been working on figuring out what's the impact, the economic impact of urban heat islands. Also in relation to the global climate change. And essentially their findings are that the urban heat island effect can have quite a significant impact on the economy of a city. So again, this is something that I think is very relevant for Singapore, especially Singapore is a city-state, so if the city is in trouble, then the whole nation is in trouble. So from this, I think generally urban heat island effects is getting more and more attention here in Singapore, and I guess elsewhere as well, and I think this article is just one example of that. So that is really just sort of pointing out again the urgency to look into this issue of urban heat island effects. And then what we try to do in the Cooling Singapore project is essentially three major things, and I've already mentioned some of them. The first one is, of course, a roadmap with mitigation measures. So in a sense, what we are trying to do with this is we try to provide actionable knowledge for the decision makers. So we're not telling them what to do and how they have to develop the city. Ultimately, they have to decide on their own, but we want to be able, we want to give them knowledge that we will put together in this roadmap that will help them to make better informed decisions. That's sort of the idea behind it. And then this part here, roadmap for R&D, is something that was particularly highlighted by the NRF during the early discussions about Cooling Singapore. For them, the question is, if we really want to tackle this urban heat island problem here in Singapore, this challenge, then there's also the question is, where are we lacking? What sort of knowledge gaps do we have? What are the technology gaps? And where is probably research funding wisely spent? So I think this is something that they are very interested in. And then the third one I already mentioned is the Urban Heat Island Task Force, which mainly consists of agency partners. We have, I think, all major agencies involved in the task force. I'll mention a bit more about this later. But we have also colleagues, for instance, from A*STAR and also NUS, Professor Wong, for instance, involved. And it's really the idea is to bring all the sort of experts from the different agencies, but also from, I mentioned NUS and A*STAR, together in this one group where we can have workshops, regular workshops, and exchange information and sort of also learn a bit more about the constraints that they have, perhaps from a regulatory point of view. Because, as I said, the idea is here to develop a roadmap, so we really need to sort of understand the regulatory framework which we're working in. Just briefly about the project itself, we have roughly 4 sort of components or work packages, if you like. The first is about science and facts, and this is very much about mapping, heat mapping. It's about taking the data, taking the facts, what we have, and try to generate heat maps. I'll give some examples. And then, of course, the work package 2 was also mentioned earlier. This is where SMART is heavily involved. This is about assigning gaps, and that is really focusing on mitigation strategies. The third one is on policy, and this is really on sharing insights in the roadmap development. This work package in particular is very much also about the Urban Heat Island Task Force. So with one of my colleagues, Constant van Aerschot, so he's really busy talking to the agencies, keep communicating with them, and it's getting them together. That's quite a major effort. And then the fourth work package is actually hasn't started yet. It will start a little later. This is about prototype development, and here we're currently thinking along the lines of web-based applications and visualizations. And the idea is that these web-based applications would go together with the final reports and the mitigation strategy reports, what we will produce until the end of the project. So you will get printed material, but there will also be sort of an online version, which is more interactive and I guess more fun to use. Okay, just I give you a rough sort of walkthrough of the sort of thinking that we have. It's generally a multi-scale approach, and I'll just give you an idea. So on the macroscopic scale, of course, I won't go into the details of solar irradiation and thermal storage. We heard of this before. Of course, the anthropogenic component is also very important. So this is a Sankey diagram showing essentially what happens with the energy that is imported into Singapore. And obviously, we want to know where the energy is being consumed, or where it's used, and where heat is being generated. So here, on this level, it's very much about the energy balance, and there is no. I put temporal into brackets because actually we could have especially here, of course, you have a temporal pattern there. But there's no spatial resolution. And this is important to sort of estimate the total UHI in terms of energy. But then, of course, it's also more important to know where are things happening. Where's things happening? So, for instance, as I said, we don't have a spatial resolution here, but then would be on the mesoscale. This is essentially where we have those heat maps. And these would be essentially tempospatial distributions of in this case, energy usage. That gives us a better idea of where it's basically about the anthropogenic component of the urban heat island effect. And this, if it works, the video, that should, well, it would show you the traffic. Unfortunately, it seems it's not working. But essentially, it gives them one example of sort of like the tempospatial distribution of energy consumption in the traffic. So you would see in the morning rush hours, you get a peak. And then, of course, in the evening rush hour, when lots of traffic is on the way. This is about the buildings. This is, I should mention this, this is based on work by colleagues from TUM Create and also a former colleague from FCL, Matthias Berger. You may know him. So this is, again, is about the energy fluxes, but on the buildings. And then on a micro scale, I guess it's really on the neighborhood level. We've heard already about Orchard. In Orchard, the anthropogenic component of the urban heat island is actually quite high because of the density and the energy consumption there. And then, of course, when we come to the micro scale, this is also the importance for the outdoor thermal comfort. At the beginning, we had this discussion: is this project just about urban heat island effects, or should we also talk about? Should we also look into outdoor thermal comfort? And at least to me, this all goes together. I mean, obviously, urban heat islands is at some point affecting the outdoor thermal comfort. So, of course, this would be then on a much smaller scale than if you just look at the. Oh, I think I pressed the wrong button. Let me just get back. Yeah. So this is also something that we look at. And I mentioned here a measurement engagement campaign. So this is something that we are currently planning to do. And we will probably carry this out sometime in between August and October. I'll get to the timeline later. But basically the idea is that we wanted we thought, okay, if we want to think about outdoor thermal comfort, then the best thing is we should actually go out there and talk to people, conduct surveys, and collect data. The measurement campaign will also have sort of check and balance kind of a function because we're currently also using the National Science Experiment data, which I think some of you are already familiar with. The problem with this data is that these are some handheld sort of sensors that are being used by students, primary, secondary school students, and there's a big question about how reliable this data is. So we wanted to take some of these data, bring our own sensors, and just get a better idea of how much we can trust. And at the same time, interview people and get a better idea of the qualitative or intangible aspects of it. So for instance, perceived control is one component, intangible. So that's essentially how much do you have choice to walk somewhere where it's in the sun or where it's shaded. Also the expectation, of course, plays a big role. If you're expecting that it's going to be warm, then of course if it does actually make you sweat, then you probably still don't feel as uncomfortable because you were expecting it. So we're trying to get a better idea of outdoor thermal comfort, but at the same time then relate this to the urban environment. So we'll be looking into probably in the CBD area. There will be some measurements be done in an HDB area to get a variety of sites. Okay, so as I said, the project sort of started at the beginning of the year and is well underway. We have been, in fact, the last 2 weeks, I would say, it's extremely busy for us because just 2 weeks ago we had our Cooling Singapore launch. That is a bit strange, perhaps, because the project started at the beginning of the year, but we had the launch event only mid-year. And the reason for that is that the NRF urged us to only do this once we have assembled this Urban Heat Island Task Force, because this is really an important aspect of the project. And it took us a while to get all the agencies together and essentially form this task force. That's the reason why the launch was only 2 weeks ago. And then just next Monday, we will have the first workshop, the first Cooling Singapore workshop. And the focus on of this workshop will be the mitigation catalog that has been prepared over the last few months by my colleagues. And then, as I said, around between August and October, we will conduct this measurement and survey and an engagement campaign. There will be another workshop towards the end of the year, which will most likely focus on tools, the tools that are being used to evaluate different mitigation strategies. And yeah, but at the moment, it's really, that's the next big thing. So I think everyone is extremely busy at the moment preparing for the Monday workshop. And then this is just an excerpt, just to give an idea of how this catalog actually looks like. This is only a draft. And it's obviously a lot more pages than this, but this is just an example, a sampler, if you like, of this mitigation strategies catalog. So we will have a comprehensive catalog giving an overview of all different kinds of mitigation strategies. And the focus here is tropical climate. So we have only included those strategies that are really relevant in the context of Singapore. And then for next year, we will have, at the beginning of the year, it's planned that we have our scientific advisory committee visiting us. And then because of that, we will probably also have a third workshop there, which makes sense since they're around. And then mid-year is going to be very, very important because there will be the World City Summit, and we are planning to attend. So we're currently in discussion with the World City Summit organizers to have Cooling Singapore prominently included in the program. And this is month 18 of the project, and this is also sort of the end of the main part of the project. The project is actually 24 months, but over the last 6 months, it's really mostly developing those tools and those prototypes that I've mentioned earlier. So most of the work will happen during the first 18 months, and this is why it just nicely coincides with the World City Summit. So this is why this is a really important month for us. This was just an overview of the project. And I'd just like to highlight again the people that are involved. We have in total 8 PIs, and one of them, and then Leslie Norford, of course, is one of them, and also Li Shancheng. And then we have in total 16 people on the team. We also have a couple of interns. And I just want to highlight the smart people. You probably already know them. Juan Angel Acero, Gloria Pinata, and Mohamed Omer Mughal. This is the team from SMART, and then we have roughly equally sort of distributed the manpower across the different institutions. We have also a number of people involved from the FCL, from the Future Cities Lab. They are strictly speaking not part of the Cooling Singapore project, but they are still part of the whole Cooler, Calmer Singapore sort of initiative that we've been working on at FCL. So by all means, they are, in practical terms, part of the project as well. So there's quite a number of people there. Okay, this is one overview. I think there's some time for some quick questions.
Yes.
I think it's up without the microphone. So I have a question regarding how much of the heat island effect is due to changes in vegetation and albedo and those factors, and how much of it is due to this emission of anthropogenic heat from buildings and traffic. Do you have a sense for that?
Yeah, this is exactly one of the things that we're trying to really get an idea of what exactly is the problem. I mean, obviously...
So that's not known?
Well, it depends. So if you're in a high-density area, then the anthropogenic part plays a big role. Obviously, if you're in a less dense area, then the anthropogenic part is actually not that high. So, for instance, in the area where the Flux Tower is, Matthias Roth, they have just published a paper on this, and there the anthropogenic part is actually pretty negligible. So it's really mostly about the heat storage from the incoming solar radiation.
Because I think understanding that would dictate what kind of strategies you need to look at, right?
Yes, this is exactly the part of the work package 1 where we try to do this heat mapping so that we get a better idea of sort of the areas that we should look at, but also the components, whether it's more the anthropogenic component or the solar irradiation part, for instance.
And also, I think if the latter is the case, if the reduced vegetation, for example, is the factor, then we have to be very careful because in defining what is cooling. Because if you increase vegetation, you may get the urban heat island effect down, but you may get humidity.
Yes.
And so you don't impact the.
Yeah. So then this also affects the outer thermal comfort, right?
Yeah.
So this is why I said I think this is all part of one bigger picture, and what we're trying to do is sort of tackle it from a holistic point of view. But yes, we are still working on the sort of the findings and the outcomes.
All right, thank you. Our next speaker is Dr. Negin Nazarian, who will be speaking on numerical modeling of urban climate.
Thank you, Professor Thompson, for the introduction. I'm privileged to speak today and elaborate more on the talk by Professor Nurford on the urban climate analysis, and also explain what is our effort at CENSAM to achieve a comprehensive analysis. And what we mean by a comprehensive analysis is to have an evaluation that can cover a wide range of physical processes contributing to the urban climate, as well as maintaining the scientific accuracy, but doing that also in the efficient and not too complex manner that can potentially be used by designers and decision makers. So for the purpose of today, and also some of our work mentioned here, we're going to talk about the numerical modeling approach. And I just want to add that even though we are only talking about the numerical tools, they are vigorously validated with the experimental measurements that we have. And we also hope that they work in parallel with the measurements of the urban climate to further inform the modeling as we develop them. So a more narrowed down mission of what we're hoping to accomplish. As the title of the talk also mentioned, our goal is to understand the micro-scale urban climate in more depth and then learn how we can use this information to then inform the mesoscale modeling. So microscale, which is the scale that you and I would interact with the climate and also get affected by climate in terms of emission, heat, and so on, is in the order of the meter, but is very much affected by the urban climate in the neighborhood scale, as well as the mesoscale. And the urban characteristic at these levels, they all affect the holistic urban climate that we experience. And they go both directions. What happens in the urban street canyon microscale affects the larger scale and vice versa. So for the purpose of today's talk, my talk would be on two parts. First, I would talk about one of our projects on microscale modeling, and that's focused on thermal comfort. And the second part would be on an example of how we use microclimate analysis for informing mesoscale modeling, and that's done by urban canopy parameterization. Okay, so first part, thermal comfort. And that's something that probably it's somewhat tangible for us living in Singapore or even for a short visit. Is this room too cold for you? For me, it is. And it's one of the concerns that not just on daily basis of outdoor environment or being indoor with the AC, but also it's on the news and headlines warning people that there are hotter days to come. And the caption of this figure actually reads that the temperature can be unbearable at times. Wearing lightweight fabrics is a smart choice. And this is due to the strong or the important impact of thermal comfort on health. And even though this concern is very tangible to us, but actually quantifying thermal comfort is rather complex because it depends on various parameters. Not only the air temperature, but also how much you're exposed to the sun, the wind speed, humidity, and as well as your metabolic rate, and even other subjective preferences of thermal comfort, as I mentioned, that some may agree that some range of temperature is comfortable for them and the others disagree. And there are metrics that we can summarize these parameters into one number, mostly normally defined by temperature. And our work so far has been using standard effective temperature. And I'm showing an example here. There is a range of temperature that you can quantify. Okay, if the SCT value is within, let's say, 21 to 26.7, then you're in a comfortable range, and then your feels like would be hotter or colder as you move in different directions. And then this metric would be dynamically changing by factors like wind velocity or how much radiation is you're exposed to, which is indicated by mean radiant temperature. And mean radiant temperature is actually one of the most critical factors to be modeled. And now I'm introducing the model that we have developed in SenSAM OTC 3D, Outdoor Thermal Comfort in 3D. And a big part of this model is about numerical modeling of mean radiant temperature. And that is the reason that it's a very complex factor is that it depends on many geometrical parameters and also surface material properties. Here I'm categorizing it on three main factors. Surface visibility would be one of the first factors. If you're walking in orchard and exposed to surface that's highly reflected, that would be a different story than walking in an open area. And as you move along a street, your visibility of different surfaces would be very different, and also those surfaces may be having different reflective properties, different temperature, and so on. Second factor is the sky view factor, how much of the sky at any pedestrian level that you're located you would see, and what does that mean in terms of the radiation exchange in terms of both long wave and short wave. And lastly, the shadows. Are you in the sunlit or are you in the shaded areas? And in the model that we have, we are able to calculate the mean radiant temperature in high resolution by looking at these three factors. So here I'm showing the schematic of how at every pedestrian point, they're using the schema based on the Tiangong Yale, also postdoc at SenSAM, we were able to calculate both visibility of different surfaces as well as the sky view factor. And similarly, calculate in high resolution what would be the sunlit and shaded areas. So one aspect of the thermal comfort model that we have is, and what we think of it as an advantage, is the modular approach that it takes. That instead of developing a model that does all the aspects of urban climate analysis, we rely on the modular approach, which means that this model can implement a work done in energy balance modeling, urban 3D model, and urban flow that has been developed for decades in the field, and use them in very different scales and different resolutions. So for example, for the urban models, we can use it with the parameterized way of urban density, or we can we have implemented the Python library that Professor Norford mentioned before by Dr. Chen to get the more detailed 3D model of urban area. Similarly, for energy balance, from the very resistant-based nodal points to very detailed temperature distribution of the urban surface can be inputted, and as well as the CFD simulation that will give you the detailed urban flow. And this is also something that we're putting more effort on to make these processes more automated. So we have different models that are developed by different community or within our group, and they each have their own strength and limitation, but when they can be combined together, they would give us the comprehensive analysis that we are hoping to achieve. So for example, one of our efforts right now is that we would like to have detailed evaluation of outdoor thermal comfort, as I mentioned. And let's say we have this location in the NUS U-Town, and we want to see what is the distribution of thermal comfort here. Let's say if you want to put a student activity there for a few hours of the day. So we have this thermal comfort model, and it requires certain input. And we've linked that with the energy balance model that will give us the surface temperature. And this is an in-house model, temperature of urban facades, indoor-outdoor building energy balance. But then this model itself has certain limitation that comes from the radiation balance, and it can only deal with more idealized configuration, which is not suitable with the site that I'm mentioning here. So we're now working on co-simulation of this model with a much more elaborate radiative exchange model, DART, by that also one of the collaborators, Dr. Tianyang Yin, is in our group. So we are trying to facilitate this cross-model communication between them so that depending on the case study or the parameters of interest, we can use them together. And this is one example of how we have used the OTC3, the thermal comfort model for a neighborhood in Singapore, using the workflow of getting the 3D model by Chan et al. We got the 3D model of a neighborhood in Singapore, Sengkang, and then also used the energy balance model that was developed in the ETH group at CREATE to get the surface temperature, and then found the distribution of thermal comfort at different hours of the day. Similar to some of the previous effort that Professor Norford showed, this model is meant to be open source, and we have already included it in the GitHub platform. So it's still an ongoing process, but as you can see here, there are some documentation and examples that will lead you through how to make some idealized geometries or more elaborate 3D model to use or to calculate thermal comfort. So like any other numerical model, what we have developed first is ongoing, and second is always have some advantages and some limitations. The advantages I tried to cover throughout the talk. The modular approach would allow it to be used with a wide range of tools, and it also has a more accurate representation of radiant exposure with high resolution, and also the flexibility in the resolution of the inputs and the geometry implementation. The one main limitation that we are currently investigating is on the representation of vegetation and water body, and also to be able to dynamically calculate the humidity at different points or the pedestrian locations. Additionally, this model only takes into account the microclimate parameters that comes into thermal comfort. As I mentioned, there are a wide range of factors coming from the psychological perception of thermal comfort, and currently these are not integrated. And we looked at the automation with other energy balance model, but we still haven't assessed how it can be automated with CFD, mostly because of the computation cost of the airflow assessment. So last point I want to mention about this is on getting, or our current work, future work of getting more meaningful results from what we are calculating with the OTC3D. And that comes into context of outdoor thermal comfort autonomy. So how, instead of just having one map for a distribution of thermal comforts in a location at a certain time, we want to be able to know how this space is performing throughout the year. So how autonomous is this outdoor space to keep itself in the desired thermal comfort range without the need to add additional shading, additional cooling equipment. And that's a metric that you can define based on the percentage of the occupied time that are within certain range. And we are currently trying to work to also optimize the calculations that are done in the thermal comfort analysis to be able to get this output instead of just having the one, or having a spatial distribution that would also have the temporal representation as well. And with that, this is the last slide to talk about the thermal comfort. I would like to talk about now our other efforts where we try to use the information we have or the knowledge that we have on the microscale to inform the mesoscale modeling. The work that we have done is with the computational fluid dynamic simulation of microscale, and I have here an example of, let's say we want to do a mesoscale modeling over Singapore, then you would have presumably a domain this size that would also be nested with larger scales. But in this domain that covers Singapore, you would use a grid size that are often in the order of, let's say, from 300 meter to 1 kilometer squared. And that means that when you are looking at these grids, even though you can distinguish which of them are over land, urban, or not, but what happens is that the two grids next to each other one might be covering a place like downtown core in Singapore, and another one Geylang neighborhood. And these have very different urban characteristic, and they also have very different climate, as also mentioned by the even UHI variation of different neighborhood in Singapore. So it is important that even though we're not able to go down to this scale of street canyon and resolve what's happening there, but have enough knowledge to parameterize these characteristics in a different way so that we can represent them in the larger scale urban climate analysis. And this is another representation of let's say, the mesoscale grid that you have. It's big enough to cover a range of microscale and neighborhood scale phenomena that contribute to air quality, thermal comfort, energy consumption, and so on. And the way that we do this parameterization, and what would be the focus of the talk going on, is on using urban canopy parameterization and a multi-layer column model approach. What it means is that it gives information on the parameterization at different heights and different layers, and parameterize for certain effects of buildings and tree, like what is the drag, what would be the turbulent kinetic energy, and the budgets. And to just put that in the context of where does this multi-layer urban canopy model comes in compared to, let's say, CFD or other bulk approach, on the left we have a representation of what the CFD would give you, which is a 3D distribution of the urban flow. And on the right, we have the bulk approach, where you would only represent the urban canopy and what is happening on there with only one node. And the urban canopy model is in between, where it can represent more processes and still is more computationally efficient than what the CFD would achieve. So you have horizontally averaged parameterization at different heights. And this is a work that has been developed for the last 15 years or so, and it started by Martilli et al. 2002, and the use of CFD models, it dates back to 2010, and ever since the drag coefficient, tree foliage, and the radiation and energy balance have been parameterized. The model does well in comparison with the measurements, but there are cases like this when I'll just mention that this is what's now known as BEP3 with this consideration of the both trees and the radiation. But when it was compared with measurements, and this is one of the examples that are showed over Vancouver, you can see that the model has higher temperature estimated than what the measurement is. And now we're looking into what are the factors that are contributing to this overestimation of temperature, and how do we solve that? So we found that the overestimate of temperature is because of underestimation of vertical exchange, and our solutions are as follows. First thing is that, as I mentioned, CFD models are used for the parameterization, and this is the CFD model previously used, RANS. And compared to the other more sophisticated turbulence models like LES, it doesn't represent the full flow characteristic. So our first solution is to use a more sophisticated turbulence modeling of urban flow for parameterization. The second, in simple words, we want to add more physics to the parameterization scheme or the formulation that we have used. There were certain processes previously in the parameterization that were assumed to be negligible and not considered, and now we are, with the measurements, we understood that they're actually not negligible, specifically with high-density urban areas, so we're adding those parameterization as well. And the third factor would be to integrate the effect of details of surface heating. In reality, we have surfaces, some shaded and some sunlit, and we are trying to integrate what would be the overall effect of this as opposed to considering uniform surfaces. And lastly is to integrate the effect of surface inhomogeneity. So we don't have always idealized arrays of building, we have height variability, we have also spacing difference, so these are the factors that we want to focus on. And so far, the first two have been implemented, and also the last, some of our other colleagues have focused on. And we are currently in the process of evaluating the last two factors. But I will show you some of the results of what we obtained. So this is the LEA simulation done over a realistic neighborhood in Vancouver. And this simulation, it covers the area that is surrounding a flux tower in the Vancouver Sunset area. And the goal eventually for these mesoscale models is to represent or be able to get closer to the realistic urban neighborhoods. And now we see that with the improvements that we have with the LES-based urban canopy parameterization, which is the dashed blue line here, we are getting much closer than what the model was before in some of the important characteristics of the urban canopy. And we are doing further analysis to integrate the other factors I mentioned to modify the parameterization. So with that, I would like to conclude. So our goal, as I mentioned in the beginning, is to achieve a comprehensive urban climate analysis. And so far, we've been working on different aspects of either model development or using the current model or improving them for achieving that. And this here, I also have a very short overview of what are the other projects that we have today. They are categorized in four main topics of urban ventilation, urban energy, thermal comfort, and urban canopy parameterization. And for today's purpose, we mostly focus on that. With that, I would like to thank you and open for questions.
One question. While Dr. Velasco gets set up, we can take one question for Dr. Nazarian. Yes, over there in the edge.
Hi, thanks for your presentation. So it's very interesting, like your model concept about the short wavelength radiation and with the different shading design, the shading impacts. So I'm wondering whether your numeric modeling concept about the building material, like the long wavelength radiation, that's, so how much do you think how much temperature will change? That's because the long wave radiation emitted from the building surface or vegetation?
If I understand your question correctly, you're wondering how we are integrating the effect of material properties and specifically on the differentiate between long wave and short wave radiation.
Yes.
Okay, so the part where I mentioned the surface visibility and how that comes into effect, that part is actually very important that we also integrate the effect of surface properties. If you are close to a building that is highly reflectant or has a high temperature, both in long wave and short wave, that would affect the mean radiant temperature or the radiation exposure of the pedestrian. So in the modeling aspects, we try to make it in a way that the model can take in those input for material properties and also do that in a separate way for both long wave and short wave. And this will allow also doing sets of either sensitivity analysis or evaluation that can be done to look at the effect of design, look at the effect of these materials on the flow. And I would just add that it is very significant. And just to add to that, there is also a recent measurement study done at the Arizona State University that we currently using to validate some parts of the model, and that has specifically shown that the horizontal radiation, both long wave and short wave, has as much effect as the radiation coming from the sky or the sunlit area. So these factors are integrated in the current model.
Okay, thank you.
Up next, we have Dr. Eric Velasco, who's going to talk about battling air pollution and climate change in Singapore.
Hi, everybody. Good afternoon. It's my pleasure to have this opportunity to talk about our work. This photograph corresponds to 2 years ago case episode 2015. Please forget. Please don't put attention to the photograph for 3 seconds. And how many of you consider that Singapore has problems of air quality? Please raise your hand. Wow, this is a great change. I made this question 7 years ago, and nobody raised a hand. So let me start with the talk. The first step to solve the problem, how to solve the air pollution problem in Singapore, is with a great team, with an international team formed with colleagues, professors from Singapore and overseas, and a bunch of students. And clear, with the great support of our mentors, Professor Brian Lam and Dr. Luisa Molina. Sorry? What's going on? Oh, yeah, I saw it. No? Yeah. And obviously, with the great funding from National Research Foundation. Thanks a lot. And well, I joined CENSAM in 2010. I was given the task of develop a research area on air quality and climate change mitigation at city scale. And well, this was the information at that time. There were only PSI readings, 24 hours pollutant standard index readings, once per day, and only annual concentrations of the 6 criteria pollutants. Wow, that was a big surprise, and not a good one. But well, you don't have to, this announcement, this advertising in the newspaper say a lot. When insurance companies start making business with lung cancer, something wrong is happening in your city. And well, there were scientific evidence that the asthma rate is a big problem. 1 in every 4 teenagers of Singapore suffer of asthma. It's true, asthma can be triggered by many reasons, but one of them is air pollution. So, our first task was to conduct a comprehensive assessment of the air quality conditions in Singapore. Our conclusion was that we didn't have enough scientific information. We didn't count with air quality data to conclude if Singapore counted with good or bad air quality. Not many people like our results. Not many people like our conclusions and marked us as bad men. But these people didn't know that bad men really know how to have fun. So then in 2013, the first case event after the big event on 1997 came. And well, at that time, we didn't have too much data. At that time, we have data only 24 hours. The dissemination of data improved a little bit before 2 years after our review paper. And the agency started releasing 24-hour average concentrations. So, but the case came and the people didn't know what was happening. The air quality information needs to be timely, needs to be there to provide security to everybody. So people started asking, what's going on, what's happening? So we take the publicly available information of air pollution, we did back engineering, and we demonstrated that, this is the bottom. And we demonstrated that with using only 24 hours average data, we were showing this information. We were missing the really, really bad spikes on pollution. So after 10 months, of our demonstration, NEA started releasing hourly readings of fine aerosols concentrations. This was something very good. And how many of you commute every morning by public transportation? Great, you're a great audience. Well, I'm sure that you have experienced those huge plumes coming from diesel buses, diesel trucks, traffic, etc. So we don't have to, yes, Singapore, the worst events of air pollution are triggered by the massive wildfires on neighboring islands, Sumatra and Kalimantan, but also on our daily activities, we are exposed to other sources of pollutants. And one of them is while commuting every day. So we took inspiration of this good movie from the 80s, and we designed a number of experiments to evaluate the exposure and the inhaled dose while we commute. We have been conducting several experiments. One of them was along Orchard Road. We evaluated the exposure and the inhaled dose when we decided to go from Plaza Singapura to Ion. That's a transect of 1.5 kilometers. We evaluated different transport modes, public bus, MRT, taxi, and walking, and 8 different metrics of the aerosol pollution. Mass concentration of PM1, PM10, PM2.5, ultrafine particles, that those are the real relevant particles. We shouldn't be talking anymore about PM2.5. In a modern city like Singapore, we should be talking about ultrafine particles, particles with a size below 100 nanometers. The problem with those particles is that they go directly to our lungs, and from there they can translocate to any part of our body. PM2.5 are important, but they end in our nose and in our throat. And well, when we evaluated the inhaled dose, yes, exposure concentration is relevant, but it's more important to consider the effort that we do when we commute. It's very different when you go sit in a public bus, or when you have to walk quickly to go to your office or to your school. And we found that MRT, at least for that part of Singapore, the cleanest mode of transportation is by MRT. And well, we show our preliminary results and results from another study at bus stops with the media, and that was on November last year. And on January this year, by first time, the Minister of Environment recognized that Singapore has problems, that Singapore is not meeting its air quality targets. And on that day, the minister implemented new emission regulations on diesel transport. That's something very good. We have taken our portable instruments to different cities, to Bangkok, Ho Chi Minh City, and Mexico City too. In Ho Chi Minh City, we ran a very neat experiment. We evaluated the efficiency of masks, and well, we found that even industrial respirators are not capable of filtering all particles coming from traffic. And these results confirmed our hypothesis that these are the real effective masks to remove against the malignant PM2.5 during the haze events. And Heiko, let me correct you. The first Interproject project was this. That was conducted in 2013. That was a very nice experience. At that time, colleagues from ETH, they were doing an experiment. They have a very nice study on how to improve walkability along Little India. And they wanted to include the air pollution as a parameter. So we went for some beers, good wine, good discussions, and we put together our knowledge. We combined their knowledge, their expertise on topology, on urban planning. I put my expertise on air quality monitoring, and we came with a very nice project. We were able to map air pollution at ground level at a very fine resolution, 20 meters. And even we designed a monitoring station at ground level for that neighborhood. This was a very nice experience. Let me change gears. Now let me move to climate change mitigation. We have been measuring fluxes of greenhouse gases, carbon dioxide, and energy, as Professor Norford mentioned before. And well, we have been using eddy covariance flux towers. Eddy covariance is the most direct technique to measure fluxes to the atmosphere. It's a direct technique, it's a direct measurement. It's not an indirect method. And in addition of doing good science, we have been trying to also to be doing good diplomatic work. And some of you may be familiar with this figure. We combined our flux measurements with other approaches, and we came with this partitioning of the carbon dioxide emissions to the atmosphere for a low-rise neighborhood of Singapore, Telok Kurau. And our most relevant finding was about vegetation. Yes, trees, large trees, mature trees, they are the guys doing the work. They help to remove carbon from the atmosphere. Yes, but we cannot remove soil respiration from the equation. Soil respiration is very important, and in the case of Singapore, where the weather is warm and humid, soil respiration tends to, microorganisms below ground tends to be very active and make that of greenery an emission source, not a sink as everybody thinks. So more greenery, not always, helps to reduce carbon dioxide. And since our findings, we have been conducting a series of new experiments evaluating the soil respiration. Our results, also we went to the media, we shared our results, and 1 year later, there were new regulations to protect mature trees. Energy balance, with the flux tower, we also measure the energy balance. During 7 years, we have been building a tall and beautiful wall. Oh, sorry. I want to say long and beautiful database of micrometeorological data. And we have been making teams with the real modelers, with those who are developing the models, with those that are getting dirty their hands, that are proposing new approaches, new theories to understand, to improve the current models. And well, we are working on it. It's a long-term vision. It's not at 2 years. It's going to take us several years. We are working on it. And unfortunately, nowadays, things are moving very quickly. And everybody wants to get results tomorrow or in 2 months. And this is happening with many urban climatologists. They think that to run models is like, and getting data for their models is like going to a supermarket and filling the basket with all the needed input data. Then they put everything in a black box, and voila, they are ready to cool Singapore. They can build catalogs of control measures. I don't think this is the correct approach. And let me conclude, finally. How to battle air pollution? We need scientists, competent scientists. Those scientists need to be very honest, transparent. Our work has to be very transparent, and we need to learn to be patient. This is a long-term fight. It's not 1 or 2 days or 1 year or 10 years fight. This is has to be a sustainable battle. And please, it's not about key performance indicators. It's not about writing papers, making longer your CV. It's about making changes. It's about making impacts to the society. Try to improve to improve the quality of life of everybody. We need to demonstrate trustworthiness. And my last recommendation, work with journalists. Approach to the media. They can help you a lot. They are the best vehicle to communicate, to translate our work, our scientific knowledge to the society. Thanks. Please, if there is any question, comment, is welcome. Yep.
Why don't we see more electric vehicles?
That's a good question. If you go to other places, for example, Norway has the highest rate of electric vehicles. Oslo has the goal of remove all gasoline and diesel cars in, I think it's in 10 years, something like that. We should, and we should think in, yes, electrical vehicles more, but more than that, we should be thinking in public transport, in massive public transport, trams, subway, etc., etc.
All right, great. Thanks, Eric. So our last speaker for this session is Professor Jason Cohen, and he's going to be speaking on a new approach to quantify and constrain biomass burning in Southeast Asia and East Asia. And following this, we'll have a brief Q&A panel. We're going to shorten the time a little bit to make up some time lost, but hopefully that will engage us in some cross-talk discussion. Thank you.
Okay. So thank you all very much. It's a pleasure for me to come back and to present. I'd like to thank all the people. So many of you I've learned a lot from and have guided me for a long time. Some of you, like Chan Wang and Paolo Rizzoli, I knew even when I was a PhD student at MIT, even before I came to SMART. And then when I came to SMART, I met many more of the MIT faculty. And all of the wonderful scientists that I've spoken with, like Eric, the speaker before, and Benjamin, and many of the other people that we work with day to day. And of course, El Fatih as well has provided a lot of very deep insights. And so I really want to thank all of you. Now, some of you have seen me talk before know I put in a lot of photos. I put in a lot of photographs that I take. So each photograph is meant to represent some of the science and to try to explain some of the impacts. So this is, as you've seen before, one of these large images of smoke from fires taken over Indonesia that spread all the way to the horizon. So just as a very quick overview, what are aerosols and why should we care about them? So these are tiny particles, liquids, solids, mixtures of the two, and they impact us. They impact the energy stream, the climate system, and visibility by scattering and absorbing and extincting radiation. They are chemicals, which, as Eric mentioned before, if they get into our lungs and into our bloodstream, they can impact our bodies. They impact the hydrological cycle, and Wang Qian is one of the world's experts on this topic of how aerosols impact rainfall. And although some of the sources are natural, the large majority of sources in Southeast and East Asia, and South Asia as well, are anthropogenic in nature. So in this part of the world, we as humans are one of the largest causes and sources. And so it would be very good to figure out what these impacts are. Okay, so some of the first cut work that we've done on this was using a Kalman filter, integrating metals and measurements together from around the globe. And we came up with, lo and behold, that the optimized values for black carbon emissions should be a factor of 2 to 3 greater than what the modeling communities have been using. And in addition to this, the impact is not equal in all places. We found that Southeast Asia and East Asia are two of the areas where the emissions are most underestimated throughout the whole world. Okay, well, being based in this area of the world, it's important. So when we feed these new emissions through the global scale models and we run with them, we do an order of magnitude better, the root mean square error, against measurements as compared to, at that time, Bond et al. Data set, which the IPCC was using and the community was using. Great. So when it comes to sort of like an annual average value, we've taken a step forward. Perfect. And this makes sense given all the economic growth that's happened in East Asia, Southeast Asia, and parts of Eastern Europe. No surprise. Okay? But there's still a lot that was wrong and was missing. So one of the things we need to do is we need to look, what's different? Where do the particles come from? Well, we have urban sources and we have fire sources. In these regions of the world, dust is not a very important source in Southeast Asia or most of East Asia. So we focus, what's the difference between urban and fire? Well, urban sources are reasonably quasi-steady state over a long time period. Cities do grow, and therefore there may be changing in the economics, but these changes are relatively slow. So we can look at cities, but we need to look carefully. Why did I put up these two pictures of Qingdao taken in 2003 and in Sapporo in northern China taken in 2014? The answer is both were not considered polluted areas. If you go back and you look, the city of Qingdao had emissions of 0 in the initial IPCC emissions data sets because it was considered not a city at that time. Of course, it's a city of 5 to 6 million people, one of the top 10 largest ports in the world. So including it's relatively important. Same thing, everybody looks at Japan as being clean. This shot was taken by another former MIT alum, taken of me using my camera, Arniko Pandey. And as you can see in the background, the northeast island of Japan is heavily polluted on this day, at this time. We didn't realize it. We just looked later back at the photo and said, wow, okay, good example. Great. Now, urban areas do, as Eric pointed out, have variation on very high time frequency scales. But a lot of the variation is due to changes in meteorology, precipitation, and certain nonlinear chemistry and physics that occur. So I'm going to point out an example of this. This is me at Sun Yat-sen University. I was just traveling there to visit. And 3 kilometers away, this tower here, the Canton Tower, is about 600 meters tall as a reference point. 2 days later, I'm going to show you a photograph from the top of the tower looking back at Sun Yat-sen University 3 kilometers away. This is me on the top of the tower. Here's Sun Yat-sen University, this green area here. 2 days later. Obviously, a huge change. And if you look at the hourly measurements, which are in black, versus the daily average measurements, which are in green, you can see that, yes, there are spikes that occur somewhat randomly as you get shifts in meteorology, changes in the boundary layer. So on day-to-day or hour-to-hour timescales, on the urban scale, you have to look. So the question is, how do we improve our knowledge? We can do the modeling, do inversions at annual timescales, great. But if we look at data on hourly or daily timescales, it's too much data, there's too much going on. Can we find a sweet spot in the middle somewhere? So let's look at fire sources. Fire sources are highly variable, but they're variable on an inter or intra-annual timescale. There is not a burning season when it's wet. The burning occurs during the dry season. And because we have some ability to predict when the dry seasons will be, we have some ability to constrain. Also, once the fires start burning in this part of the world, they tend to burn for very long periods of time. It's not just a single fire burns, gets put out 12 hours later. Okay? But we have other issues that we need to consider, such as how do we look at clouds and smoke which are obscuring the sources from being measured, or how do we deal with the buoyancy issue because you have heat co-released with the particles. So here are all examples of fires which were not seen as being fires. In all 4 of these cases, there were no Motus fire hotspots found in any of the regions, for all the reasons I've mentioned. This area here over India and Nepal, the smoke was so thick that it was all being treated as cloud by the model, by the satellites, and therefore there were no fires. In this case here, which occurred in China, it wasn't picked up as well for whatever reason, likely because the ground surface temperature was too low. Here, in non-burning Malaysia, I caught a fire. There's no Motus fire hotspot there. And in Indonesia on this day, it was completely cloud covered for 200 kilometers in all direction. So clearly our ability to try to quantify these emissions, even using inverse modeling techniques, we have to overcome a lot of challenges. So instead of doing the traditional approach, I've been trying to develop a new approach. And right now I've developed an emissions data set, which is still under review, so I don't want to put it out, which is a completely new take on fire emissions from around the world. And we're validating it with models and measurements here in Southeast Asia and East Asia. So as we see, if we look at the satellite data from 2000 to 2015, we can see that there is a lot of variability that occurs. Here's Southeast Asia and East Asia during the burning time here. And so if you look at certain places, you can see that the variability is very different as a function of the meteorology, as a function of the season. So how do we use this information? Well, if we do use this information and we do some data analytics with it, we can get out regions of extremely high variability. So this has been published, and as you can see, one of the world's largest areas of variability is here, Sumatra, Borneo, and Peninsular Malaysia. Now, as you can see, there is an intra and intra-annually varying time series. Certain years, like 2006, 2015, 2013, are more intense. Other years are less intense. Sometimes it's longer duration, sometimes it's shorter duration, but it's every year. Okay? Here is one of the world's other largest variable areas, consisting from Bangladesh, Myanmar, Thailand, Laos, Vietnam, and out over the South China Sea. Now, clearly the South China Sea is not a source. The South China Sea is a receptor. So you have to be careful. How do you pull apart your source region from your receptor region if you're using measurements in a top-down sense? If you just rush and say, aha, our measurements show here's the region, but there's no physical science basis for assuming that the South China Sea is a source of emissions of smoke particles. So you have to be a little bit careful when you do this. Okay? So when this work was put together, looking that with this new approach, we can build a model. This is the model result, which roughly match the measurement I showed you 2 slides before. The correlation order of magnitude for the RMS error is very low. And we can catch intra and interannual variability, as compared to the GFED approach, which is what the community is relying upon now and has been relying upon for a long time. GFED and FIN offer similar results, where the spatial distribution is wrong and the intraannual variability is wrong. Great. So at monthly timescale now, we've got a product. But monthly timescale is not good enough for what we're looking at. For example, you can look here. These are daily measurements taken from Calliope, which is a LiDAR satellite. It beams laser down, and you can look at the height. And if you look, fire and non-fire regions are very different, as we'd expect. But if you actually look at the heights on a day-to-day, you can see there is a large statistical difference. Over burning areas, the average plume height goes from roughly in the upper end of the boundary layer up to 3 to 4 km high. And over non-fire regions, most of the plume is found within the boundary layer. As I said before, you have different buoyancy due to different heating. The physics is correct. This is all measurement, but as you can see, day to day, while there are statistical consistencies across this time period looked at, day to day, there's still a lot of variation. So monthly based averaging, while it's an advance, is not sufficient. We'd like to get slightly higher resolution if we really want to understand what's going on with the system. Okay, so this is, one of these works as an ACP, the other is still an ACPD, but you can go download them and take a look. Okay, so let's stop just looking at aerosols. When we burn things or have emissions, we co-emit multiple chemical species. Let's use some fundamental chemistry knowledge with measurements. So in addition to looking at aerosols, I'm now looking at trace gases as well. So here is the global annual value for, 14 or 15 years from the OMI satellite. Okay, we can zoom in on Asia, and you can see Singapore, Kuala Lumpur, Bangkok, the Zhujiang Sanjiaozhou, the triangle area from Guangzhou, Hong Kong, and then you can see South Korea, Japan, China. All the urban areas are showing up. Great. So the point is we want to integrate AOD with the trace gas measurements together. We want to put the aerosol and the gas measurements together. Because if you're looking at sources or urban areas, while the ratios are different, the different chemicals are being co-emitted. Okay? Now we can also look at the data differently. Instead of just looking at the means, we can look at the extremes. And when you look at the extremes, you can see some of these urban areas don't show up because their extremes are not as high. They're constantly polluted at a moderate level, but they don't have extreme peaks. If you look, Borneo and Sumatra show up very well on the extremes map, whereas they don't show up at all on the mean map. And as you can see, certain areas, the big cities, like Beijing actually doesn't show up on the extremes, but down from Beijing does show up on the extremes map. So we can look at the same data using different approaches. And in addition, let's also look at land surface variables, because if we are going to be clearing the land and burning it, as we know from the peatland studies, we'd expect large changes in the land surface variables themselves. So we can do this, and we can make more maps, and we can put relationships between our pollution measurements, the trace gases, the land surface, and we can come up with some ability to predict on weekly timescales. Not daily yet. Weekly timescales, we can now have some predictive ability, inter and intra-annually varying. Okay, great. So, what are some of the next steps? This is work which has been submitted or to be submitted soon. The first step is let's include additional trace gas measurements. So now I'm throwing in additional measurements from MOPIT, which is a different trace gas satellite. And as you can see, we can do some of this analytics and we can break up the results into urban regions. Urban regions, in this case, would be downwind of cities in Thailand and Vietnam, in some of the major Chinese urban areas. And we get, this is over many years where this data has been done. And you can see you have an annual cycle along with variability that goes along the way. But if we look instead at those areas that are associated with fires, we have a completely different set. It's much more variable. Why? Because you have peaks, and the peaks occur in different times in different locations. So now we have multiple satellites that we can use to give us more data to teach our models better. In addition, we normally, when we look at remote sensing, we look at total column loading. Here's a map of the 15-year average total column loading. And as you can see, okay, fine. You have sources from Bangladesh, Myanmar, Thailand, Vietnam, southern China, parts of Korea, etc. Okay? But if we look at the 700 millibar level, and why do I say 700 millibar? Because we're in the lower free troposphere here. What is going on? We have a massive signal at the 700 millibar level. Why? Okay, so we can put together our multiple satellites, our gases and our aerosols. They give us different pictures of what's going on. They both are from the same sources, but different impacts. And then you can look to do this, and you can see that by combining all the information together, we can look at source versus transport. So we put this into the models, and we run the models, and then we do comparisons. So we've compared the new approach, which gives us number of days we're able to represent fire from the model that match with observations from Aeronet, LiDAR, and ground stations far downwind. These are the different stations and different new approach approximations. We're able to match from 8 to 12 fire days per month. Using GFED and FIN, at most we can match as 5 fire days per month. Additionally, the correlation is much improved with values as high as 0.9 using the new approaches. Whereas the largest FIN GFED correlation we get is 0.7. In that case, they don't match any of the fire days. And when we look at the modeling, when we look at the surface, it corresponds well with the chemicals that we are associated with direct fire emissions. When we look at the column, it corresponds very well against the column measurements like the MODIS. When we look at the 700 millibar, while the color and the strength is slightly low because the emissions factors are still too low, but we see it looks similar to the 700 millibar measurements that I pointed out before. And statistically, this is all consistent and all there. So, what does this mean? What's going on? If we look at a dynamic, in this case, we're having large sources that are originating from Bangladesh, Myanmar, Thailand, Laos, and Vietnam. Due to their buoyancy, they're rising up and being transported downwind over the South China Sea, over China, over Taiwan, over Korea. They're being picked up at stations in Taiwan, in Hong Kong, and even as far as Korea. The measurements are being picked up. But the surface concentrations aren't very high. It's all being exported in the lower portions of the free troposphere. Hence, one of the reasons why the emissions are being underestimated, because it's not being picked up at surface stations, which is where most people are looking. But eventually, due to gravity and due to settling, it will deposit back down. Okay? Now, these are, when you look at the vertical distribution of measurements over different areas, from Chiang Mai, where they have a super station for LiDAR, and at Hong Kong, you can see Hong Kong, the same period of days, they have these large-scale plumes in the lower free troposphere. In Chiang Mai, they extend from the surface up to the lower free troposphere. So we're able to reproduce these measurements in the vertical reasonably well as well. So, in terms of some conclusions, in addition to wanting you to all get ready and start implementing this new emissions data set, which I hope offers a new perspective and allows us to do better. In addition to the space and time, and as you can see over the South China Sea, far away, filled with smoke from 2014. And here's an old picture I pulled out from Beijing in 2005 to show we actually have been doing better. When people are talking how bad are the levels in Beijing now, this one was worse. So we have some hope. We can do better in the future. But it's not just issues. For example, we're underestimating in terms of the total amount. But that amount that we're underestimating, while on average maybe 30%, actually in the very bad years is a huge amount. We're talking hundreds of percent in the very bad years. In addition, when we combine, we can now reproduce at weekly timescales reasonably well, which provides an additional underestimate. But it's not just the total amount that we're off by. There's a spatial temporal shift that we're also not catching. So if you have a value of 0, you can multiply your value of 0 by 1,000, and you're still going to have 0. If you don't update the spatial temporal map, you can scale all you want, and you'll still get the wrong result. okay? And so we need to look at this comprehensively. Now, this is just the very first cut at this, so any suggestions, improvements, et cetera, I'd be most happy to hear. Thank you all very much for your time.
Okay, great. So at this time, I'd like to invite the speakers to come on down to the stage, and we're going to have a 10-minute Q&A session. And perhaps we could start, if there's any questions while people are coming down, we could start with any questions for Professor Cohen. Yes, Benjamin? Oh. Go ahead, there's a question.
So if I understand correctly, you're using a different sort of satellite observations to get that data set.
I'm using multiple satellite observations, plus ground station columnar measurements for aerosols and trace gases.
So you can't have the sort of resolution you would get with hotspot time-wise, but you get better.
Time-wise, I'm not sure what you mean. If you're talking hotspots, you can get at 1 kilometer resolution. But in many of these regions, you see no hotspots, but there are clearly sources. So I'm taking a trade-off. I'm saying I'd prefer to know the spatial temporal distribution at tens of kilometers rather than have complete gaps. Because the hotspots, if you look, and I've checked before, since I've been in Guangzhou, I've seen hotspots that occurred on my university campus that were not fires. Also, when I was in Hong Kong, I saw hotspots that occurred in Hong Kong Central that were not fires. And yet in other areas, there are large-scale fires where there are no hotspots. So my approach is completely different. And the model results, I think, match the measurements, including far downwind, much better. And therefore, I think we as a community should move away from using hotspots for now until we can find a way to better improve the weaknesses that are associated with them, at least based on my findings.
Okay, thanks.
All right, terrific. So are there any questions then that span the talks in this session? Please go ahead and start firing them off. Paula, yes.
And the sentence that I'm referring to, I was intrigued, consideration of psychological perception of thermal comfort. That is a very, how would you quantify or parameterize a psychological perception, if there is any way?
That's true. Yeah, just to reiterate the question, the consideration of the psychological parameters in the thermal comfort assessment, the way that we are doing it for numerical modeling, is missing. It's because due to the fact that we are only focused on the microclimate parameters. If you want to focus on that, it's normally done by surveys that you go out and on top of doing the measurements of, let's say, mean radiant temperature, air velocity, air temperature, you can also survey people on getting there are also metrics that they quantify the thermal votes, how comfortable they feel in a location. And also, in addition to that, somehow measure the behavioral changes that they would do. So if this is a comfortable enough space that they would remain here, or no, they would decide to remain here but move to the shade, or no, they would decide to move along. But so far it's been only done with the surveys and campaigns in real environment.
And do you obtain a number of a big number statistically significant, so you can do some correlations which are meaningful? Because to interview people, you need to interview very, very many to have statistical significance.
Right. So, for example, there is actually a study done specifically for Singapore, coming out of the ENEAS group, that they looked at, let's say, going to parks or botanic garden, and they tried to cover a wide range of pedestrians or people that are spending time with that. It is true that that number has to be significant, but even with the starting number that they have, you can see certain trends that the votes for comfortable at certain time of the day, for example, is higher than uncomfortable and vice versa.
I have a question for Dr. Velasco about, you seemed in your conclusions a little bit critical about what people should do before they get into schooling at Singapore. So what kind of studies, what kind of proposals are you referring to when you made that comment?
When we talk about climatology, we are talking about long periods of time. That's the difference when we talk about weather and when we talk about climate. First is to have a long-term vision. We need to collect data for a long period of time. That's my first point. Secondly, Singapore is a unique place. All the work so far on urban climatology has been conducted in mid-latitude places. Europe, United States, Japan, a little bit in Mexico, but in the tropics it's almost zero. So we need, and the conditions here are very different. Just you need to go outside and you will feel the difference. Everybody runs models that have been developed for Phoenix, for instance, where the environment is very dry. You go outside and you will feel that it's not the temperature, it's the humidity. So we need to learn about latent heat. We need to learn about evapotranspiration. And we cannot expect that people from Europe are going to come to teach us how to do it. We need to develop our own tools. We need to learn about it. And that takes time. It's the work that we need to do. We cannot continue doing copy and paste. It's basically what everybody likes to do nowadays. The softwares are there available. You can go to the NCAR website and download for free the software, Word, or you can, if you have a good budget, you can buy MBMed, for instance, and then voila, the models are going to give you figures, numbers, but are those numbers correct? What are they telling you? Do you have data to validate your results? So far, the results that we saw from the urban heat island, they have not been widely validated. If you don't have energy balance data, a long period of time, forget about your urban heat island and thermal stress results. We can discuss later about that.
Question here in the back?
It's in response to how Eric is very critical about modeler. I kind of do agree that we do not have enough data, but the thing is, we have to build. So we will just have to make do with the best information we have. And especially in the Southeast Asia region, no matter what you say, the science is not there, the data is not there, but people is going to build. So what would you suggest that the people who needs to build do? If you think that the models are not good, what should we be basing our design on? Yeah, so I think that's the more problem that we have to talk about.
Let me reply your point, and it's a good point. Go to the field, observe, measure, and then run models. Live from your comfort, the comfort of your office. Sweat a little bit. When we design experiments, projects like this, we need to put together models and measurements. We cannot separate. We cannot just plan models and then find somewhere, ask where you can go to the supermarket and get the data to run your models. You need to start side by side, models and measurements in a long-term vision.
Yeah, just wanted to follow up on the modeling issue, which I think is a very important and a very valid point. One thing that I actually noticed from the presentation is Sensem seems to make a conscious effort to put your models and what you develop on GitHub, and hopefully also very well documented, so that if someone leaves, then someone else can pick up the work. Because one of the things that what I've noticed in the past with all sorts of models, I mean, people develop models, And then there's this one person who really knows the ins and outs of that model. Let's say a PhD student, and then the person graduates and then is gone. And then typically also the knowledge what's in the model, if you're lucky, some of it is published. If you're even luckier, some of it is documented. But just reusing existing models is often very problematic. So what I think what also needs to be done is really thinking about how to make models that are being developed more accessible to other people. And so if people are leaving, for instance, that the models don't just disappear. Model interoperability is another issue. Let's say you have a model for this component and another model for another component. This model is written in some obscure language. This other one is something proprietary where you have to pay thousands of dollars for to get the software. So putting them together is often also a problem. And then, of course, the whole validation part. If you use a model that works in Europe for typical European cities, and then you try to apply it to Singapore, then obviously that also gives you a lot of trouble. So I think, especially when it comes to modeling, there's a lot of work that needs to be done. But not so necessarily so much on developing the models, but also, as I said, sort of managing the models.
I'd like to just quickly throw in with the last two questions, the person in the back as well as Professor Altair. I really think that starting as a modeler myself, and I still do mostly modeling today, but try to use data, we need to look holistically. We need to use the best tools we have available now, but we need to look at them. Every single model we have and every single measurement we have has error associated with it. Some of the errors we have some information about. Some of the errors we don't even know about. But we need to objectively look, what do we do well? What do we not do well? Can we reproduce? Many people just use statistics. Do we reproduce the mean? Well, what about your variability? What about your skewness? What about your changes? Can we reproduce the extremes? What's missing physically? Read broadly, understand. If we realize the physics is out of date or the chemistry is out of date, be willing to accept that we may have to trash the models we're using now and adopt something better. So it's a matter of don't just use them as black boxes. We should always constantly be striving to improve our metrics that we use our models to compare against. We shouldn't just settle for what's been done before. But of course, you said, what do we do in the meantime? Well, we have to do something. But if we understand what's going on behind it, maybe we realize we can do something better. And I guess this even gets to Prof. Rizzoli's question of people's thoughts and people's perceptions. On the air pollution issue, this is another big deal. What are people's thoughts and people's perspectives? And there are many studies that give cutoff levels for certain things, but what are people's thoughts and perspectives? There are some people that insist they'll go running every day under all conditions. And then sometimes they'll say, oh yeah, it's a bit polluted out. I feel pain in the lungs. Maybe I shouldn't go running today. I don't know if any such surveys have been done, but it comes down to perceptions again and getting information out. Okay, WHO has studies. There are many studies that have been done, great. But does this get through to people? What are people's perceptions? What is it that makes people want to make impacts and decisions? They're not basing it on models, they're basing it on other factors. And I don't know either how to address it, but I think that's a very important point. And it looks like Prof. Norford wants to
Well, this isn't so much on Jason, what you had, but just one thought I had. I want to pick up on something that was in Heiko's presentation about the World Cities Summit next year. In the U.S. at least, I think a number of cities are assuming more of a leading role in combating climate change if it's not going to happen at a national level. And I think from perspective of Singapore, it's easy to say, well, whether it's urban livability or climate change or air quality, well, it's a small country. There are local problems, but globally it's just a drop in the bucket. And I don't think that's the right perspective. I think Singapore is a major city, as are a number in China that Jason showed, and others. And I think for sort of the future of mankind is largely cities-based, as we're hearing. So I think C40, World Cities Summit, Rockefeller Foundation, 100 Resilient Cities. There are a lot of efforts that are embracing Singapore, where I think that what goes on here can be part of a greater whole, and hopefully with more democratization of data and proven models. But I'm somewhat optimistic that what Singapore is facing, what we're trying to do here, can benefit from what others are doing elsewhere and have reciprocal benefit, as Eric is doing in Mexico City. So I think we're a world of cities, and I think the national boundaries are maybe less important now.
All right, thank you. Well, this has hopefully kickstarted what will be a fruitful continued discussion over the coffee break.